Okay, so, well, today our exercise is going to be about yield spatial temporal stability. Before we start that, I just want to quickly mention to you all about the exam that's going to be next Thursday, yes, February 27th, so a week from today. I just want to, maybe I mentioned this in the previous class, but I just want to make sure everyone is on the same page. So for the exam, it's going to be on ELC, and you're going to have to use the computer from the computer lab. You are not allowed to use your own laptops. So just be aware of that. And because of that, you will have to come to your computer lab to do it. You're not going to be able to do remotely from elsewhere. So next Thursday, it's going to be 2 hours. You need to come to the computer lab. You're going to use the computer lab computer, not your laptop. It is closed book. Um, let's see. Well, there's going to be different types of questions, multiple choice questions, short essay, mix and match, true, false, those types of things. Everything that we covered in class, anything that I wrote in a script that we developed in class, anything that was part of a lecture, anything that was part of a reading assignment or any assignment for that matter, all those things are fair game. I am not a tricky exam giver, I don't think. I'm not going to be asking you things that we never talked about or that we maybe talked about once. I'm going to be asking you things that we've done a lot that I would expect you to know it by this point. So remember those things. Anything that I ask you in class when we're having conversations, those are the types of questions or some of the types of the questions that we may have. Some of the content is going to be precision ag related, obviously, and some of it's going to be code related because this course is a mixture of precision ag and coding. So you're not going to have to remember full code from memory. I don't expect that, not in the exam, not in your real life when you're working with real data. I will, however, expect you to know some of the functions and to understand some of the things that happen. So for example, I may give you a ggplot code with a few words missing and give you an output from that code. And then you should be able to know how we would generate, what are the words missing in the code that I give you to generate that output. So things like that, things that tell me that you understand the concept, but not necessarily that you have simply memorized it. But again, things that we've done a lot, functions we use a lot, arguments we change commonly, those types of things on the coding side are fair game. Let's see if I'm forgetting anything. Mhm. Can you see that again?
Like, in what topic?
Oh, yeah. So Amandeep asked until what topic is going to be the exam. If we finish this exercise today, it's going to be until this today's topic. If we don't finish, then it's going to be until last class, which is basically until yield interpolation. So we'll depend on our progress today. I really wanted to include today's as part of it because I think it's a nice stopping point for an exam to include. But that's my goal. If we finish today, which I think we may finish today, then it's going to be up until today. All right. Any questions? Any other questions? Any questions in Tifton? All right. I don't hear anything, so I'm assuming no questions. So we're going to get started with today's content then. So I pushed to GitHub a new script. So if you downloaded GitHub after I emailed you earlier today, you already have the latest version. So I asked you basically to get the files from GitHub. It's just a script. And I asked you to paste that script in our current project. So if you have done that, then under 07 EOD monitor, you would have now this. Oh, wait, I guess I forgot to actually copy here. So I'm going to have to do that. Yeah, I don't have it. So let me actually do what I'm asking you to do. So on class code, you just bring that yield stability partial from GitHub to your EOD 7 or 07 EOD monitor code folder. All right, so assuming that you did that, we're going to start coding today. As always, if you do not have your 07 EOD monitor project open, then launch that through the rproj icon to make sure that you have all the file structure correct. Okay, so a quick recap here is that, so we took 3 years of yield data, raw yield data. We calculated, or we first wrangled them, cleaned them with 5 filters, and then interpolated them, right? And this was part of your assignment. I have not checked your answers for the assignment to make sure everyone got within a range that makes sense. But I'm assuming you all did, and if you didn't, you know, we can go back to that afterwards. But assuming that everyone was able to create the interpolated EO data for 19 and 20, which again was part of your assignment, then today on this exercise, we're gonna bring the wrangled, cleaned, interpolated version of EO data from 2017, 2019, and 2020. And we're going to do some analysis here. Let me see, I don't have the correct script, so let me actually open the right script here. Yield stability partial. All right, so our goals for this exercise are to read in these 3 interpolated clean yield data for 3 different years. We're going to create year-specific spatial stability areas, and then create spatial temporal yield stability areas as well, and export this last product that's related to yield spatial temporal stability. So, okay, I think we have some conversation here on the code about why we're doing this. Ideally, we have an assignment coming up that is for you to read a paper on this topic, which will happen. Ideally, we would have done that assignment before this class, but I know you already had another assignment from this class that was due. And so I did not want to overload you with 2 assignments at the same time. But the next assignment that's coming up is going to be for you to read a paper that talks about yield spatial temporal stability and how at least that paper went about it. Before we start coding here, I just want to tell you a little bit. I guess I'm getting a little bit ahead of myself on the spatial stability topic. But why is that important? Since you have not had a chance to read the paper yet, because I have not sent that to you, I guess I just want to talk a little bit about it. So let's say that you get a EO monitor data for a crop. Let's say in our case, it's been cotton, and it is for a given year, right? So you have this data, you wrangle, you clean it, you interpolate that map, and then you look at that yield map, and you think, okay, I see that on this part of the field is low yielding, on that part of the field is higher yielding, and then here is like medium yield levels for that year. Great. That gives you some indication of what parts of the field are higher or low yielding. However, is that enough for you to really know about that field? Most likely not, right? So a few things cause trouble here. So for example, let's say that the year that you have that EO monitor data was an exceptional yield, exceptional yielding year. Let's say that rainfall was sufficient. There was a lot of cloud-free days, so a lot of photosynthesis. Everything was perfect. Nutrients were perfect. Management was well done. It was just an exceptional year that most of the field did pretty well. What if you actually got the data from a previous year where maybe there was a drought, or maybe the timing of the rainfall was not what would be the best, or maybe something else happened. Maybe a hurricane came through your field and significantly decreased your yield potential because I don't know, it had an impact on flowering or maybe on boll formation, whatever it is. The thing here is that from year to year, there is variability. For a given field, there is variability, especially related to weather. And in a good year, let's say a good weather-wise year, maybe some parts of your field are going to be high yielding and others may not be high yielding, even though the year was good. Maybe in a bad year, your whole field is poorly yielding for whatever reason. Or maybe there are parts of your field that some years are high yielding compared to the rest, and other years are low yielding compared to the rest. So there is this variability in yield, spatially within a field and year, and over time as well, over multiple years. So the more years we have data for in a given field, the better, because then we have a better idea of these fluctuations from year to year that depend on that year effect, which again, if we're talking about the same field, that fluctuation is mostly due to weather differences from year to year. Could also be crop differences, right? So let's say that this year you are on a cotton peanut rotation, for example. So if you grow cotton this year and next year you grow peanuts, those crops are different crops, right? We shouldn't be able to directly compare their yield levels on a pounds per acre basis because they're different crops, they have different magnitudes of yield, and so on. And so because of these differences on year and also on what crops are grown in a given year, we have to have a better way to bring all of this into a comparable footing. We have to be able to compare different years, different crops, and still be able to learn about yield potential across your field. That's what this exercise today is all about, is stability of yield in space and time and how we go about it. All right. So if you come to the setup chunk, I think you have all these packages already, so it should be pretty straightforward to just run them. And I guess before we start coding, let me give the chance if anyone has any questions about this concept of yield stability. All right. So as we're going to be doing that analysis today, I think maybe you're going to understand better what we're talking about, and feel free to ask questions at any point. All right, so the first thing that we have to do here is, so in this case, we have 3 years of yield data, right? So we're going to use those 3 years of wrangled, clean, and interpolated yield data that we created in different scripts, right? Just to remind you, for each one of the years, we had 3 scripts, one for wrangling, one for cleaning, one for interpolation. So in total, we had 9 scripts that produced the layers we're going to use today. And I just want for you to think about that as you go about your own research, to understand that, the more modular you make things, the more manageable it becomes whenever you're doing it. So it's a good idea to not have one huge script that does all of this for 3 fields, but to kind of break things down and make it more manageable on your side as well. Okay, so first thing, we're going to bring the interpolated, so the wrangled, clean, interpolated yield for 2017. Let me ask somebody to help me here. Let's begin today with Polly. Polly, what do you think? How would you import that layer here?
We would use read.sf.
Okay, so read.sf. What about now?
Double dots slash. data, and then date clean.
Clean? Is that the one you want to bring?
We would use the interpolated data.
Sorry,
The interpolated.
interpolated, right? Yes, I agree with that. All right, thanks, Polly. So if we run this and we print it, so we have, well, at least I have, you may have a little bit, no, well, you may have a little bit of a different number of cells here just because of the boundary, but I have 3,848 cells and 2 columns. So IP yield, so the interpolated yield, the geometry, and then it is already coming as UTM zone 16 north, so we don't have to do anything about that. If we check the summary here, the summary yield is ranging from 300 to about 1900 for the yield for the year 2017. All right, so 2017 is in. We need to bring 2 other years. It's just the same, but different files, right? So read sf // data, and now yield 17. Hold on. Oh, I actually don't have those. I think I actually moved to the wrong folder. So let me fix that on my side. You probably already have because you did the assignment, but on my side, I forgot to move them here. So let me do that. So oops. So we need yield 20 interpolated and yield 19 interpolated. Let me move that to my data folder, and then we should be at the same pace. All right. So now yield 19 interpolated, that's what we want to bring. We run that. Let's print as well, yield 17. Let me do another change here. So I'm using the yield 19 and 20, I'm using from my boundary that I created last year, which as you can see, my number of rows are different. So this is the data that I produced last year in class. And this year is a little bit less. So 2017 I did this year. So 2017 I have 3,848. This is a difference between my boundary from last year to this year. You on your side, you should have the same number of rows for 17, 19, and 20. On my side, I just need to bring the interpolated from last year instead. So another little thing to fix here. Let me do that very quickly. On your side, you should be all good. Okay, so let me reread 2017 on my side. You don't have to do that on yours. But now on my side, my 2017 has 4,046 rows. My 2019 has as well 4,046 rows. If we check the summary, just to get an idea. So here we have for 2019, we have yield ranging from 108 to 3,058 pounds of lint per acre. And now finally, let's bring 2020. So read sf // data yield 20 interpolated. If we run that and we check here on my side, 4,046 rows. And then if we check the summary, it's ranging from 300 to about 1,700. All right, so just a few things. So now that we can take a look at the summary yield for all of the three interpolated ones, we can, I wanna ask you to help me figure out here. What was the year with the highest yield? What was the highest yielding year as I guess as judged by the maximum observed yield value?
On your side.
I mean, it could be on your side, it should be similar, I guess. So on my side, so 2017, I have a maximum of 1,900, and then 3,000 on 2019, and then 1,700 on 2020. Is that similar?
Mm.
It's not on yours?
19 will be the same.
Your 29,
Imported different.
okay.
Yeah.
So I guess first point here is make sure that a couple of things, right? So the first one is make sure the range of values is different across the years, because if they're exactly the same, then maybe you made a mistake when you were exporting. Maybe you exported the same layer or, the same layer to two different file names. So that's the first thing to check. And let me just ask those in Tifton. Is everyone having like different summaries for different years? Or if somebody's not having different summaries for different years, let me know. All right, so my next question then, just to make sure that you all did the correct steps, is all the 3 years at this point should have the same number of observations. So if you print the object, this number of rows, 4,004, at least on my side is 4,046. On your side, maybe a different number, but it should be about similar. But on your side, it should be the same number of rows for all three data sets. Which on mine here, I'm just checking, and all the 17, 19, and 20 all have 4,046 rows.
No, it's different.
Okay, so is everyone getting the same number of rows across all three data sets?
Yes.
Yeah. Awesome. Okay. So then we can continue our conversation here. So what was the year that was highest yielding as judged by the maximum yield of the yield summary?
2019.
2019. Right, that's the same for me as well. 2019 was the highest yielding. Awesome. Now, what about the lowest yielding as judged by the minimum value?
2020.
383. I actually, on my case, it's also 2019.
Same.
Oh, yes. Sorry.
Nice. So overall, we're seeing here 2019 was a more variable year, right? Because you have both the minimum and the maximum yield across all 3 years. So something for us to think about. Okay, so on my side, I have all 3 years with the same number of rows. You should have as well, although your number of rows is probably different from mine, but you should have all 3 years with the same number on your side. Why is that? Didn't we have a different number of yield data points on the raw data? And even after cleaning, each year had a different number of data points. Why do we have the same number of rows at this point across all of them?
Of the boundary.
Okay, because of the boundary. How so? Go ahead, Polly.
I think it's because we did the evaporation and the number of grids we created in the boundary was the same for all the years.
Yes, that's exactly it, right? So the reason why we have, thanks, Polly. Just to rephrase that, the reason why we have the same number of rows is because we interpolated with the same grid and the same grid size. So that means that on my side, I had 4,000, let's see here, let me print one of them again. I had 4,046 grid cells in my grid. And regardless of how many data points there were behind the grid cell, in the end, you still end up with the same number of cells because we use the same grid for all three interpolations. That's exactly it, Polly. Now, this is important again, because imagine that if we had not used a grid, we just used the point data, meaning it was not continuous data, right? As you know, the point data, if you start zooming in, you're going to eventually see a space between points, and interpolation fixes that for us. But if we use the point data, it would be very unlikely that data points, yield data points from 3 different years would perfectly sit on top of each other for you to be able to compare and say this plot here in the field across 3 years. So that's another reason why we do interpolation, is to bring everything to the same size of cell and making sure that those cells align as we're using different layers as well. All right. So I have some text here. I think we already talked about this, but every time we work with yield data across various years or fields or crops, there are a few challenges, right? So how would you compare different years or fields or even crops if they, if let's say in our case, it is cotton for 3 years, but what if it was cotton, peanut, cotton? How would you compare that? Right? So some solutions, for example, the solution here is going to be to standardize yields. What do I mean by that? Basically, we want to find a metric within that year and that site that then we standardize the remaining data of that year and site according to that metric. So there are basically 2 approaches we can do here. The first one is a numerical approach. In this case here, we're going to standardize everything on that year according to some statistical summary of that year. That statistical summary could be the mean, could be the median, could be the maximum. So for example here, let's say that we take all this yield data from 2017 and we find that the mean of the field is 1,500 pounds per acre. So then now that we know the mean of the field, for each cell that we have on our grid, there is a yield value. So now we're going to divide each one of those cells by this same number of mean yield of 1,500 for that specific year. What happens then is, so if you divide, let's say that you have a cell that the yield was 1,000, I'm just going to make something up here, was 1,623. And we divide that cell by 1,500, which is our numerical reference for that year. Now this resulting number is not pounds per acre anymore. It's basically a proportion. So if your cell yield is greater than the metric that you are using to standardize, which in this case is the mean. So if your cell mean is greater than the mean of that year across the entire field, this ratio is going to be greater than 1. However, if you have yield that is lower than that, and we will have, right, because the mean sits at the middle, so we're going to have points above and below it. So let's say a given cell yield was 1,000, and you divide that by 1,500, this is going to be less than 1, right? You can always think about this as a percentage. If we just multiply this by 100, this becomes a percentage. So if I have a yield of 1,000 on an year where the mean of the field was 1,500, it means that the yield of that cell was 66% of the average mean of the field, or the mean of the field. Right? So the same case on the other one. If we multiply this by 100, it means that this yield of 1,623 is 108% of the mean of the field. So this is one way that we have to standardize. It's a numerical way that we have to standardize. And normally the metric that is used is the mean or the median or the maximum. Now, I showed you an example here where we're standardizing by the mean, which means there are some values that are greater than the mean, some values that are lower than the mean. So the output of this standardization, if you use the mean, is going to be, so the resulting value is going to be somewhere, let's say somewhere between 20% and maybe 180% of the mean. Just throwing a number out there, right? It doesn't have to be 20 or 180, but there are going to be some values lower than the mean, some values higher than the mean, right? That's pretty obvious. Now, what happens if you, instead of standardizing by the mean, what happens if you standardize by the maximum value of the field? What is the range of values you would expect to see after standardizing by the maximum value observed in that year?
I will not, because we are standardizing with the maximum value,
Mm-hmm.
so we won't have the lower. Yeah, I want to say, if we are standardizing with the maximum value, then our range will not have the maximum.
Okay, you're getting there. You're thinking in the right direction. Yeah, let me see if maybe somebody in Tifton can help us with the thinking here. So if instead of standardizing by the mean, I standardize by the maximum value of that year, what range of standardized values would you expect in a percent basis?
I think you would get the value in the maximum quadrant, the one above 90%. The upper quadrant.
Okay, so I think you're talking about something a little bit different. So instead of going there, I want to actually let's play around. So let's say if the maximum value was 2,000 pounds of land per acre, and I divide everything by 2,000. Because 2,000 is the maximum, it means that the maximum range of standardized values you would expect is 1, which is if you go to the cell that has the actual maximum value. But because that is the maximum, there's nothing above it. So everything else is going to be either 1, or if you multiply by 100, you can call this 100%. It's going to be either 100% or less than that. If you standardize by the maximum, you don't have more than 100%, because 100% is already the maximum. Everything else has to be lower than that, right? So this is just, one idea for you to think about, that the way that you standardize, the metric you choose to standardize by has an implication on the range of values that you end up with on the standardized side. Even if the overall pattern of the data doesn't change, but the range of the data will change. So that's something to just keep in mind. All right, I'm gonna delete this example here. If you want to keep, if you did it, that's fine. Another way of standardizing, so we talked about the first way, which is numerical, and it's when you standardize by a number, right? So you say you divide all of your yield values by a given metric that you extract from that year, the mean, the median, or the maximum. You could also, instead of a numerical approach, you could take a categorical approach. So how would that look like? Some papers do this, where let's say they go and they still extract some numerical summary of the field. So let's say they do the 50th quantile, which also happens to be the median. So you take a given quantile, let's say you would take the median, which is right in the middle, right? And then you say all observations or all cells that have a yield value less than the median, I'm gonna call them low yielding. All cells with a value greater than the median, I'm gonna call them high yielding. So now instead of having a numerical standardized value like 1.1 or 0.6, now we have a column saying low and high. So you took something that was numerical, you use the metric from that distribution, let's say the median or the 50th quantile, and then you use the rule. If any value is lower than that, it's low, you call it low yielding. If any value is greater than that, you call it high yielding. So 2 different approaches. One is numerical, where your standardized output is also numerical, and one is categorical, where your standardized output is a categorical variable, low or high.
I have a question really quickly.
Mhm.
What exactly would the advantage be to using the categorical method over the numerical one? It seems to me like you're just kind of settling for less information on your kind of final summary. When would you use categorical over numerical?
That's a great question, Luke, and I totally agree with you. If you do the categories at this level, you're basically throwing away a lot of variability from the beginning, right? So, I mean, I've seen papers doing both approaches. I personally think that the numerical one is better because it gives you more information, right, at this level. And I'm trying to think of like if I can think from the top of my head one advantage of the categorical. And to tell the truth, I don't really think I can find that at this level. So towards the end of this exercise, we'll create categories, but it's going to be at a different stage of the analysis. So eventually we will create categorical variables out of all this. But I also agree that doing that so early in the process throws away so much information of that variability that I also would not advise. But that's a good question. I mean, I agree that numerical is better, and I don't know if I have a good argument for when or what circumstance categorical would be better, but it is something that people do out in the literature. That's a great point.
Thank you.
All right. So in our case, also because of the reason that we just talked about, we're going to be using the numerical approach. We could have just as easily do the categorical as well, but we're going to follow the numerical approach because it keeps more of that variability in the data until a later stage for us. All right, so I propose we use the median of the field. And I want to have a quick conversation about that. So why am I choosing the median and not the mean? So I don't know if you've seen this in another course, maybe a stats course, but I want to show you something here. So let's say this is going to be a density plot. We've seen these in other classes, so you're familiar with it. Where so here would be yield, and this is the density of that. And normally, I mean, a lot of times variables are normally distributed, and so you would see something that perhaps looks like this, right? So the mean of the field would be around here for this distribution. And the median of this field would be pretty close. It would be pretty close to the mean if your data is normally distributed. However, what if your data is not normally distributed, and how would that even look like? Let me get a new page here. Oops, that's not what I wanted. Let me clean this up. You know what? I don't remember now where I clear this up. Maybe I can create another slide. Okay, well, anyways, I can just draw on top of this one here. So let's say that our EO data is actually distributed maybe something like this. So it has a high peak somewhere, but it's skewed to one side, or right skewed or left skewed. What happens with that is the mean of any distribution is highly susceptible to outliers. So outliers will be points on this very long tail. You probably have a point somewhere here that is pulling this tail all the way to the right. But most of the distribution is to the left. So if you have outliers, the mean is going to be pulled with that outlier. So for this orange distribution here, the mean may actually be somewhere here. because there are some points pulling it away. The median, however, will still be a central tendency here. So the median is not as impacted by outliers than is the median. Sorry, the median is not impacted by outliers as is the mean. So if your data is normally distributed, mean and median are pretty close. If your data is not normally distributed and it has a long tail to either the right or the left, then your mean goes with that tail. The median does not. So the reason why we're choosing the median is because it's less susceptible to outliers. Not to say that our yield data has outliers. I think we checked and it seemed, at least the interpolated distribution that we saw on the last class for 2017, at least that's the one we saw in class, was pretty normally distributed. But I think using the median kind of puts you in a safer place, because using the median, you're going to be good whether the data is normally distributed or not. Using the mean works if your data is normally distributed. It may not be what you want if the data is not normally distributed. So that's why we're going to use the median here, and I just wanted to create some intuition about why. Okay, so we determined that we're going to standardize by the median, and we're going to get the median for each year separately. Okay, so let's begin with 2017. So we're going to start off here with our yield data for 2017, which is called yield 17 or yield C17. We're going to extract, so if I just print yield 17 below, just so we see it, the goal here is going to be to have a column that has the median of the entire data set, of the entire 2017 data set. How would you do that? I think we've done different pieces of this in different exercises, so maybe you already have some intuition of how that would happen in code. Maybe let's begin by what function would you use? Let's see. Benedetta, what do you think?
We have a column just with the median. I
Okay.
think I would use mutate.
Yes, awesome. I totally agree. Because we're creating a new column, right? So we do want to have mutate for that. And just before you continue, I just want to propose a name for this column that is standardized across all of us. So I want to call this column median yield underscore LBAC. This is what I want to call it. And now what function do we need here, Benedetta?
And we call the column that we want to I think we don't know, we call the column and we do equal to.
Okay, so I think we need something else before we ask for the column name. Anyone else can help us here? Median. So Amandeep said median. There is a function called median, right? So we need to say that we want the median of something. Which column do we want the median of? Marco.
EP yield in pounds per acre.
Yes, absolutely. That's what we need.
That one, yes.
Perfect. All right, thanks everyone. So if you just run that and you print, now we still have our yield column, we still have our geometry, but if you click on the right arrow here, now we have another column that is called median yield, and it has the same value across all cells. So this value is the same for everything. The reason for that is because we asked it, because we did not group by anything. We just said, give me the median of that column. There is just one median value to be extracted, right? There's no grouping here. There's no like, oh, give me the yield, the median yield of, I don't know, according to another column, which we don't even have in this data frame. But there's no group here, meaning that we only get one median value for the whole 2017 year. And that single value is repeated for every row under that column that we created. Cool. All right. So now we have our actual yield data that is changing from cell to cell. And we have our metric that we standardizing each one of those rows by. And this metric is the same value for all of the rows. Now, how would you now do that? What is the code that you would use to actually do the median, or the, sorry, not the median, to do the standardized value of each cell by the median value as well? Let me put a pipe here, and I'm gonna just hold on for a second here and ask if somebody can help me here. Maybe Aman. What is the, let's begin small. So let's talk about the function. What function do we need in this pipe for? Mutate, right? So every time you're creating a new column, think of mutate. I want us to call this new column SY for standardized yields equals, now what? Let me go to TIF10 perhaps. Let's see. Mohit, what do you think?
We can take the mean.
So can you tell me what column names would you combine here?
IP yield,
Okay, perfect.
LBAC.
So IP yield, then what? Polly, what do you think? Can you help us here?
You divide by median yield, pounds per acre.
Absolutely. That's exactly what we need here. So we're basically dividing this column by this column. On the column on the numerator, it is our actual interpolated yield, which changes for each cell. On the denominator, it is the median, which is the same value for the whole field, right? So if you run this and reprint it, and you inspect that column now, so this column, at least the values we're seeing are like 0.91, 0.97, right? So it's that range that we were talking about before. This range is going above 1. We're just not seeing any values here that are greater than 1, but there's like 4,000 values on my side. I want to propose we do a couple things here just to get this more standardized. So one thing I want us to do is just multiply by 100 to make this as a, because right now it's a proportion, right? I want it to be a percentage. So multiply by 100. Now we can say this is on a percent basis. And then the next thing I want to do is to round it. I really don't care about all these decimal points here. I really just maybe want to have one decimal point. So something we can do is write in, I mean, it could be a new mutate. It could be inside the same mutate. I just want to come here, call the same column name because we're going to override it. And if I want to round that number to 1 decimal point, do you all remember what function we use for that? Round, right? Pretty intuitive. So round SY, I just want to have 1 decimal point. So we just say 1. If you run that and you print it and inspect, now we have exactly that. And then lastly, so at some point in this exercise, we're going to combine the standardized yield of 2017, 2020, or 2017, 2019, and 2020, all in the same data frame. So if I'm calling all of them SY, I'm not going to know which one is from which year. So with that, I want to do a couple of things in the next step. One is going to be to only select the columns that we really care about, which in this case is just the standardized yield. That's what we're going to need to do the spatial temporal stability analysis. So I just want this column and the geometry, really. So I want to add a pipe called dplyr select, and then we're going to call here our SY, but I want to rename this to SY17. So we know it is the one from 17. So we need to say the current column name is SY. I'm selecting and on the fly renaming it to SY17. And the geometry is what I want to keep. If you run that and you print it, that's what we get. All right, so we just finished standardizing one of the years, 2017. Any question about it?
Can you please draw a line?
All right, so next year I want to make one map to look into the standardized yield over space. So I want to visualize what we just did. And also, we're going to be bringing these maps from 3 different years together in the end. Because of that, I want to create this plot, but also assign it to an object so we can call it later. So if we come here, give it the assignment symbol, we're going to start a ggplot, add a plus. If I want to show this data, SY17, what geom do I need? geom_sf, right? Because it is an SF object. geom_sf. So here we're going to say what's the data frame name. So data equals SY_17. That's the data frame name. Because it is SF, we're going to use AES to say what is the field that we want. So I want to fill it according to the SY17 column, which is the column inside of that data frame or that SF object that has our yield standardized data. Well, let's just run it, see how that looks like. So this is how it looks like. If you remember, so right now the cells have an outline. We can remove that by coming back to geom_sf outside of AES. Just say color equals NA. Color relates to that outline. So now it's a little bit easier to see. I want to introduce you to something here that is different than what we've used before. So before we've been using like if we want to change our color scale, as you know, we've used varieties a lot of times. We could use varieties here, but I want to show you something that's interesting now. Because our data has a middle point that is very clear. The middle point here is 100%, right? So 100% is in the middle of the range of this data frame. And if it's greater than 100%, then it's better. If it's lower than 100%, then it's not as good. Whenever you have these types of range of values where you have a center value that is very clear, we can use a color scale that centers around that middle point. And it has a gradient with different colors if the actual data is more than the middle point, a different color if the data is lower than the middle point. That's what I want to change here too. So let's add a plus. The name of this function is scale_fill, and it is fill because we're changing the fill on the AES. And the name of it is gradient2. The way that works here is you're going to say what color you want to assign to low values, what color we assign to the middle value, and what color we assign to high values. And then we need to tell what is the actual numerical value of the middle point. Okay, so let's begin doing that. There's an argument for low. This is the color you want the low value to be. We're going to use a hex code here that you're going to have to copy from me. So use the hashtag symbol. The hex code I want to use here is 440154FF. It is this purple color here. So we're using a hex code to refer to this color. The middle point, we're gonna call it, the argument for it is mid. So what the color I want to give to the midpoint is going to be white. So we don't have to type the hex code, just the word white is sufficient. And then we have to give a color to the high point as well. So there is an argument for high. I want the high color to be the following hex code. So hashtag 22A884FF. It's this green here. Now we need to tell this function what is in our data frame, what value actually is the middle point. So for us here, there is an argument called midpoint. For us in our data frame, the value that represents the midpoint is 100, right? Because it's the 100%. That means if a value is 100%, it means it is exactly the same as the median of the field. That's what this means here. And then finally, I want to change the breaks. Well, you know what? Let's just run at this point so we can see what happens. So this is what happens. Notice that everywhere that's white, that's because the value is really close to the median. Everywhere that's purple, it means that the value is lower than the median, and the darker purple, the lower it is. Everywhere is green, it means it's greater than the median, and the darker green, the greater it is. So it's really easy for us to understand when we have a midpoint, use color to help us understand where those things are. Because imagine if we just use varieties here, we would still see similar patterns, but it would not be as clear to see if something is larger or lower than the median, which is our metric that we're using. Notice that the scale that we get here, the color scale, so 120, 80, 40, is basically according to our own data set, which is yield 17 or SY17. And this range may be a little bit different for different years. Because we want to visually compare different years, I want to make this range fixed for all the maps we're going to make. So they're really comparable across different maps. So to do that, here inside of this scale field gradient 2, there's another argument that's called breaks. Oops, breaks. And I want to specify the following breaks. I want everywhere from 0 to 180 at every 20 increments. We're going to use the function, oh, I'm missing a comma right there. We're going to use the function seq for sequence, where you give a starting point, which for us is 0. You give the ending point, which is 180, and you give the step size, which is 20. So if I just run this seq function, it gives us this, a sequence between 0 and 180 at every 20. If we then give that to this argument breaks, it's going to fix those breaks on our color scale. So if we just go ahead and run that, and then you print it, notice how it changed that for us. All right. So a few more things I want us to do here, just to make sure we can easily compare these maps at a later stage, is I want to give this a title. This map, I want to give it a title. So for that, we're going to use the labs function. We've used this before. It has an argument for title. I just want to say 2017. Very short and sweet, just for us to know where this data is from. And then I want to change this legend title here, which because this legend is associated with fill, then here in labs, you call fill equals, and then you give a new title. I want to call this median dash standardized yield. If you run this and print it, you get this. It's a pretty long name, so I want to break line in a couple places. I want to come right before standardized and give a /n to break line right there. And the same thing with yield, before yield. So if you do this and you print it, it breaks line for you wherever you had the /n. All right, a couple more things I want to do here before we finish this plot is I want to use theme map, which is the one that basically cleans things up for us a little bit more. But also one of the things with theme map is that it places the color, or in this case, the fill legend scale right on top of the map. So to change that, we're going to add a plus and then call the theme function. And we're going to say legend dot position. I want to change it to right. So this is what we get. All right, so data visualization is very key, but it doesn't do much good if we cannot interpret it. So let's see here. Marco, what do you see here in this plot? How would you interpret this map?
The right part of the field had a lower yield, and the eastern part had a higher yield.
Okay. What about like these parts here that have lower than the median yield? We add the median yield like this. Do you remember what were these parts on that field?
They were the erosion channels.
Eroded parts, right? We also have something like on the top, we have this cluster of lower than the median yields, which I think is interesting. I did not realize that looking at the previous plots. But really looks like the best parts of this field are on the left side or the west side, like Mark was saying. I agree. At least looking at 2017, right? Now that's the key thing. And if we look at 2017, that's our interpretation. Will it be a very similar behavior as we look into other years, or is it going to change? I guess we're going to find out pretty soon. All right, so now we're going to basically repeat the same steps for 2019. So really the code here is the same as the one that we did for SY17. We just have to adapt it a little bit. So instead of us going through and typing everything again, we can go back to the SY17 chunk. You can just copy everything after the assignment symbol, like that. Let's just copy that. And then here on the 20 SY_19, give it the assignment symbol and paste it. Now, what would we need to adapt on this code to make sure that we do the correct analysis for 2019? Benedetta, what do you think?
Data equals SY19, and also the field SY19.
So, okay, so maybe let's begin on this row. Would you change anything here?
Oh yeah, the yield C19.
Right, so this we have to change to make sure we bring in the 19. On this here, I don't think we have to change anything yet. We don't have to change anything here. What else would you change here? What else did you say, Benedetta?
No, actually, I copy and paste the wrong thing. Let me search. Yeah, the SY17.
Yes, right. That's exactly right. So make sure you change the data coming in and the way that we're naming SY in the end as well. Those are the only changes we have to make. If you go ahead and run it and then print it, you know what? Actually, because we did that this way, you actually did not get to see what was the median of the 2019. So let me just put a comment right here before the select. So the pipe stops here, and then we can see what was the median before leaving that out. So the median of 2019 was 1,711. I don't remember now what was the one for 2017. I think it was lower than that. If I just, you don't have to do what I'm doing right now, but I just want to check that. So the median for 2017 was 1,200. The median for 2019 was 1,700. So a higher median value. All right, so let me go back and make sure I rerun my SY17 and just so that select takes effect. And I'll do the same on 2019 to also take effect. All right. Now I think I left you pretty much everything here on this next chunk, which is just making the map is the same thing. We're just changing the data coming in. That's the only difference. And the title, right? We're making sure the title represents the year. So if you print that. Oh, also something else interesting here is I am changing our legend. So I'm asking to remove the legend. And you may think, why is that? Because we need the legend in the map. You're going to see that later in this exercise, why I'm removing the legend here. But for now, just bear with me. The legend is still applicable. This legend still applies. That's still what we would expect to see here.
I have a question.
Yes, Polly.
Can you come again? The reason why we are setting the break sequence equals 0 to 180.
Yes, so this is basically just to make sure that we can compare all three maps across.
Where does the number 180 come from?
So this is just, so if you were to look into the individual data sets, I don't think we have any standardized yield value greater than 180. So I'm just giving like a max value that is beyond, you know what, actually, let me make something here. Because I noticed that even though I asked on the first map on this 2017, even though I gave the breaks and I said what I wanted, I still don't know if it's going all the way, because I think it would go one more notch and that would be 160 and one last notch and that would be 20. So it's not fully going from 0 to 180, I think. So let's come here and actually, if you go back to the SY17 map chunk, inside the scale for gradient 2, there's another argument for limits. And here we give two numbers. So I want to give 0 and 180. Oops, not 1. 0 and 180. And I think that is what we really need here. Yeah. So please do that. Make sure you come here on the scale field gradient 2 on the EL17 and give the limits of 0 to 180. So now, Polly, we're going to fix this on the next map as well. But then this scale going from 0 to 180 is going to be applied to all the three maps we're going to be doing, one for each year. And therefore, the colors are going to be comparable. That's the goal that we have here. So going back to our SY19 map, if you come again here on the scale gradient 2, let's give it limits equals 0 and 180. So now they're going, whenever it's going to get to a point in the script that we're going to put them all side by side. And this is going to help us to make that comparison more clear. Okay, so Marco helped me with interpreting the standardized yield from 2017. Luke, can you help me here to interpret this one, which is from 2019?
This one's a little similar to 2017. It's just the on the east side where there was a lot of low yield around in 2017, kind of along the whole right border. It's more kind of clustered on the south side there. And I think it's a little harder to see the, well, I mean, on my screen, I can see it a little bit better. I was going to say that it's harder to see the channels there where there's the erosion, but you can still kind of see them. They're just maybe a little less defined.
Mm-hmm.
But and also the west is still higher yielding pretty consistently.
I agree. Perfect. That's what I would also interpret. So another thing for us to think about it is if we do not standardize, if we make this plot with the interpolated yield values in pounds per acre, that is not a fair comparison, even if you have the same field, even if you have the same crop. The reason for that is, as we just saw, the median yield for 2017 was lower than the median yield for 2019. for whatever reason. Maybe 19 was a better yield with, or was a better year as far as rainfall, right? However, we're not interested on that. I don't want to know this is a good year or this is a bad year. I want to know for the conditions that this whole field experienced in that year, what relative to the potential of that year, the yield potential of that year, what areas are good, what areas are bad. That's our goal here. That's why we have to standardize, because even though it's the same crop, if we just use the yield data itself, then 2019 would have a lot more high yielding areas compared to 2017 because of the year effect and not because of the underlying variability that comes because of soil. Perhaps there is, eroded areas, perhaps there is a compacted area, whatever it is. That's what we're trying to get to here. And that's why we need to standardize, especially if you talk about different crops, which is not what we're doing here. But if it was a rotation, which is very common, you would have 1 year cotton, 1 year peanuts, and maybe we don't have yield monitor data for peanuts yet, so maybe that's not the best example. But think of perhaps you have cotton and corn, and you have yield monitoring both of those machines for this grower. You would have to standardize, right? Because corn it produces a lot more weight per area than does cotton. So you cannot just take that weight, that production per area, and compare directly, right? We have to standardize. All right, so lastly, we're going to do it for 2020. I also have the chunk here for us to work on. I'm going to ask you again to just copy and paste the one from this time can be the one from 2019 is the closest one. Just copy that. Let's paste it here. We have to make some adaptations as we just did above. So make sure you change yield C19 to yield C20. And then on the select, make sure you rename it to SY20 instead of 19. And that's all. And I guess, again, before running this, I want to add a pipe before we do the select, or I want to add a hashtag before the pipe so we can see what was the median of 2020. So 2020 yield median was 1,137, was even lower than the other years, right? Just so for us to compare that. So I'm going to come back here, let the pipe flow and rerun it. So I do get the effect of the select function. And then finally, we're going to make the map for 2020. And again, I want to remind you to come here on the scale gradient 2 and add the argument for limits. You want to say limits, C function 0 and 180. So our color scale is fixed across all years. And then if you print it, this is what we see. All right, so maybe can someone else help me to interpret this? Maybe Amandeep.
Like it has more low yielding areas which are scattered all around the map.
Mm-hmm.
So, and also on the west side of the map, there is a strip of like low yielding areas on the edges of the field, which is not there on the east side.
On the east side.
Yeah.
Gotcha.
There's a strip of the low yielding areas which is not in the other two maps. And also in the center part, there is more low yielding spot.
Okay. So Amandeep was saying that we have this strip of low yielding points on the western boundary. That we have some strips in the map as well that maybe we were not seeing before. We still see those eroded areas as low yielding. That maybe was not before. So yeah, that's perfect. Okay, so we're gonna run this next chunk and then I'll give you a 5-minute break. Because we're going to 420 today. So we're gonna use the package Patchwork to combine these plots. And I'm basically calling the name of each one of the maps that we made and just asking for all the the legends to be collected into one. So if you run that, this is what you should see. So all three maps side by side with one single standardized legend. And this was the reason why we left the legend in the first plot, and we removed the legend from plots 2 and 3. And we also made those adjustments on the scale fill gradients to have the same breakpoints and the same limits. So everything is comparable. Cool. All right. So now before we go, before I give you a break, I just want to ask you this. Now that you have data for 3 years and it's been standardized within each year, what do you notice as far as patterns of yield across 3 years? What would be something that really comes out to you that is like, okay, this is interesting? Let me ask Marco.
I would say that 2017 and 2020, they show the same behavior with a low yield on the eastern part of the field where there are the eroded parts, while the highest yield is always on the southwestern part of the field.
Mhm.
And in 2019, the difference between eastern and western part of the field is particularly high.
Awesome. Yeah, I totally agree with that. And something that, so the fact that we standardize the color scale across all three maps, what that does, if you don't set a range and breaks the same, what we all know that ggplot does is it takes the range of data for that plot and extends the color scale within that range. What we're doing here is not that. What we're doing is setting the color scale to represent all the data and using that set scale for all the maps, what that implies visually is that the highest color or the darkest green may appear in just one of these maps, and the darkest purple may also appear in just one of these years. And to tell the truth, at least visually, it looks like the darkest purple, which is low yield, standardized yield in relation to the median, it looks like it happened on 2019 on this part. And very interestingly, it also seems like the darkest green, which is the highest standardized yield, also happened in 2019 on the same field. Because I see darker green here and darker purple here as compared to other years. As we observed earlier, 2019 seemed to be a very divergent year for high and low yielding for whatever reason. If we were to look back into maybe rainfall data, or maybe we had some more records on management from this grower, what did they do? Did they apply more or less nutrients or pesticides or water or whatever it was? It looks like 2019 was a year where our highest and lowest happened across all 3 years on a standardized scale. At the same time, if you think about it, it looks like, I mean, even though our eyes, our brains are trained to find similarities. So, Marco did a great job saying what was similar. There's also some differences, right? So maybe some areas of this field were high yielding in 1 year and low yielding in another year. Maybe there are areas that were always high yielding, or maybe areas that were always low yielding. That's what we're trying to understand here is, are areas consistently high or low regardless of the year? Or maybe are there areas that in some years are high yielding, other years are low yielding? And those exist. So that's what we're going to investigate after. Okay, I want to go through this last chunk here and then I'll give you a break. So let's just get a summary here of yield, of the standardized yield for each one of these 3 years. So I'm going to run one line at a time so we can look into the range. For 2017, the range was from 25% of the median to 156% of the median. If you check 2019, it was from 6% of the median. Look at that. That's really low. to 178. I actually had the wrong number here, 178 of the median. So a wider variability in 2019, as we already observed visually. And then 2020, it was from 33 or 34 to 154. So really look, as Marco did a great job interpreting, it looks like at least statistical distribution, it looks like 2017, 2019 are more similar. And then 2019 really had more of the extremes, both on the low and on the high side. Okay, I want to give you a 5-minute break in case you need it. And I'll stick around if anyone has any questions, but I do want to give you a break. All right, we'll be back in 5 minutes.
I mean, field monitor data.
You're asking if every field has it?
Like every field has a picker which collects that field data
You mean in general or in this case?
in general.
No. No, so yield monitoring is, I mean, depends on the crop. So for example, for grain crops like corn and soybeans, it was first developed for those crops. So it is more common than most, I mean, all new combines have it, but there's still a lot of combines that were purchased before that technology was invented that they don't have. If a grower has an older combine, but they want to install this equipment, they can do, like, there are some ways to retrofit their current equipment. So it would be more common to see grain combines for corn and soybeans to have yield monitor. For cotton, it is becoming more popular. I wouldn't be able to tell you like what percent of growers have it, but it's definitely less than that of corn and soybeans. So this field here, that, you know, and it's not on a field basis necessarily, right? It's more like, does that grower have a picker with yield monitoring capacity? Because if they do, they probably use that same picker for all of their fields. That when they grow cotton for that, in that case, right? And something interesting is, I know Dr. Velides in Tifton did some work around developing an yield monitoring system for peanuts. I don't think that it's been commercialized. I don't think there is a commercial product for peanut yield monitoring. So there are some crops that don't even have a yield monitor, right? That would be another limitation potentially of doing these, is if you're working with a grower, they may have data for some years and not for others. And they wouldn't have that data if it's a crop that they don't have the yield monitor for that crop.
Like, it's just the recent technology.
Yeah, I mean, it's somewhat somewhat recent. It's not something that came out like in the last 5 years. It's been longer than that. Maybe 10 years, maybe for cotton, maybe 10 years, for corn and soybeans, maybe longer. But don't quote me on that, because those are just some estimates. I'm not completely sure of when this came out. But they came out first for corn and soybeans, and then cotton followed.
It's on field monitor, or do they have anything related to like seed monitoring? Like how much seed they are putting?
So that's a good question, because if you think about it, like for corn and soybeans, it is a grain yield monitor, right? In the case of corn and soybeans, it is the seed or the grain is actually what's being monitored. In the case of cotton, it is not the seed necessarily. You may not even see, like, the sensor, which in this case, for cotton, the sensor is a near infrared sensor. You may not even be able to see or sense the seed, because it's seeing the seed cotton, right? Which is like the lint with the seed inside. And then it's just making an assumption of how much turnout to use. And you can calibrate that afterwards as well, once you have the actual turnout after it's been ginned. But it's just a near, I believe it's a near infrared sensor that works on cotton pickers.
Like expensive for the farmers.
You know, I'm not sure of how much that costs. Yeah. All right, so we finished our 5-minute break. Let's resume here. Okay, so notice that we took each year, extracted the median of that year by itself, and used that value to standardize all the remaining yield data for that year, and did that 3 times, right? 1 for each year. So now we have 3 maps or 3 layers of standardized yield data that are on a percent basis. So notice that we're not talking about pounds of lint per acre anymore. We're talking about percentage of the median. We standardize it to that. So that gives us these patterns, which are the spatial variability for each year, right? So right now, that's what we have. We have spatial variability on a standardized basis for each one of the 3 years. Now, our goal is to combine these 3 maps into one. So what I want to know now is, let's say if we take one of these pixels, or sorry, these are not pixels. So let me change my wording because I don't want to confuse you. We take one of these very small polygon cells and look into that cell across 3 years. So maybe we would say, okay, this year here, this cell was, so it's green. So, I mean, at least the one that I'm trying to show you, it's green. So maybe it was like 120% of the median. And this next year is darker green. So maybe that was 140% of the median. But maybe next year it was purple. Maybe it was 80% of the median. I want to take that information into account to understand if that pixel was always high, according to the median of that year. Was it always low? Or did it change depending on the year? Maybe it was higher than the median in some years, lower than the median in other years. That's what I want to be able to understand here, is to understand the stability of yield for that pixel over time. Always high yielding, always low yielding, or does it change depending on the year?
One pixel.
Yeah, so Aman is asking, we're going to put one pixel on top of the other. Yes, that is what happens behind the scenes. Like, we're not going to see it, right? We're not going to be able to visualize it, but that's what's going to be happening here.
Medium and then we're gonna take medium.
Yes.
But if we have 2 endings and then one metric, sorry.
Well, so, okay, that's a valid question. So Amandeep is saying, what if we have an ace in one of the cells? I have 2 questions for you. One is, do we have an ace? How would you know? Well,
Yeah.
the white cells are not an ace. They are just close to 100%.
So
Yeah, no, you don't have to apologize. I mean, every question is valid. So, okay, so, but that's a good point, because what if we had, I guess, quickly telling you that if you look into these summaries here, if we had an ace, there would be a column saying an ace and how many we have. So maybe the first answer is, well, we don't have an ace, but what if we did have an ace? There's a way to fix it, right? So if you remember, every time you use these statistical summary functions, minimum, mean, median, maximum, ST, we always say NA.rm equals true. If you do not do that, and if you have an ace, you get no value, right? So there is a way we could fix it if we had an ace, but we don't in this case. Okay, so for us to do our spatial temporal stability analysis, we're gonna have to join these three data sets, but not just join them in like, let's just take the columns and stack them. Is actually a spatial join. We want to make sure that data from a given pixel or a given cell is aligned over time. So if we take the same cell in 2017, 19, and 20, and we know exactly what happened with that cell. So we want it to match spatially. So okay, so let's think about this. After we combine all these three data sets using a spatial join, which is what we're going to do in a second, imagine that now we're going to have a column for standardized yield for 2017, for 2019, for 2020. And if you think of just one row of the data set, which would be one cell on the grid, you have now a standardized yield across 3 years. How can we then combine that into something that we can use to classify that pixel as always high, always low, or changing? Ideally, I would have given you already the assignments that you're going to have next. So ideally, you would have already read the paper and you would have already have a better understanding of what I'm trying to do here. But I guess this time we're going to have to develop that understanding as we code. So here's the idea, and this is what the paper you're going to read is doing. So we take all these 3 years of data for one pixel, and we're going to calculate two metrics out of those 3 years for that pixel. One metric is going to be the mean. So what was the mean standardized yield across 3 years? So let's say that pixel you had 90%, 100%, 110%. If you take the mean of that, the mean is 100%. So the mean standardized yield for that pixel that I just gave an example would be 100%. And then we're also going to calculate, so that is the mean response over time. But how can we put a number on stability or lack of stability or instability? We're going to calculate the coefficient of variation of those three numbers, of those 3 years for that pixel. And then using the mean across 3 years and the CV across 3 years, those are the two metrics that were going to help us to then create classes to say, this pixel here was always high or always low, or it was unstable. It was high sometimes, low other times. So we're going to need to first combine these three years into one data set. So then we can calculate the mean for each pixel and the CV for each pixel, and then we'll classify them according to those two metrics. If that does not make a lot of sense yet, it's going to start making more sense when we code, and for sure make more sense when you read the paper. So let's just do that. Yes. Categorize, yeah. All right, so the first thing here is, if you come to the next chunk, I want to first combine all of these three objects that have the standardized yield for 3 different years into one. So what we're going to do is start off with SY_17. That's our first year. We're going to do our first join. We have used the function left join in the past, which left join works if at least one of your data frames, one of your objects is a data frame. In this case here, although they both have, if we think of joining SY17 and SY19, they both have data frames, but they are SF objects, meaning they have spatial information. So we're going to use that to join instead of just a column name as we use with left join. For that, there is a column called ST_join. That's what we're going to use here. I want to say that I want to join with SY_19. And then we're going to change a few things here. So it has an argument for join equals. We're going to say that we want to use the join whose name is st_equals. And don't click on the function, so don't have the parentheses here. If you did click, just delete the parentheses. I want to just quickly show you here that if you ask for help of this function stjoin, you can look into the documentation of this function. And as we'd already talked about, it shows the arguments, it shows what values they can take, and so on. The default value of the join type is st_intersects. And if you come on the arguments here, it's on the join, it says geometry predicate function with the same profile as st_intersects, see details. If you look into the details, it says alternative values for argument join are, and then it gives you a list of other types of joins here. I'm not going to go through all these and all the differences. I just want to tell you that when I was developing this exercise, I played around with a lot of them, and I realized the one that we needed for this purpose was st_equals. How did I find that out? The way to find that out is, so SY17 itself has 4,046 rows. SY19 itself has the same number of rows because it was based on the same grid size. When I did the original stjoin with the default join of st_intersects, I was getting more than 4,000 rows, and that was clearly not right, because I should just get the same number of rows after the join, because these objects are exactly the same in space. So that's how I found out. If you ever do a spatial join, I just wanted to make you aware that you have a lot of different types of joins, and you can read into each one of those types if you wish. For this case, we need st_equals. And then there's another argument here called left. So asking if you want to do a left join, just say true. So if we run this and you print this object sy all, notice that we have the same number of rows as before, 4,046. And now we have site year 17, the geometry, and site year 19. Site year. Sorry, I'm thinking of something else. Standardized yields, not site year. So we have standardized yield 17, standardized yield 19. That's exactly what we wanted. So this polygon that is right here on this geometry is the exact same in 2017 and 2019, and this is the value that it took in those different years. That's what we're doing. Now we're going to do the same thing with SY20. So we're going to join now and have the column of SY20 here as well. If you want to copy the stjoin function here, you're welcome to do that. If you don't want to type, then after that, add a pipe, hit return, and paste it. And really the only difference is that we are changing SY19 for SY20, right? So we're starting with SY17, doing an stjoin with SY19, and then doing an stjoin with SY20. If you run all that, and you print it, now we have the 3 standardized yield values for the same cell across 3 different years. Any questions or problems at this point?
Can you repeat why we put left equals true?
Yeah, so the left equals true is just to make sure that it's doing a left join. So what that means is it takes whatever comes first on that sequence as the left data set, and then uses that as the frame for the join of what's coming from the right, which is basically, so for this first join here, the left data set is SY17, and the right data set is SY19. So we're just saying take what's coming from the left, use that as the reference, and then join what's coming from the right.
All right.
Okay, so now we have in a single data set the 3 standardized yield values for each cell across 3 years. That's what we wanted. So now what is left for us is on a row, so row wise, so for each row, we want to basically calculate the mean of these three values and the CV of those three values. Normally, R does not operate on a row direction, it operates on a column direction. One function that we can use to say, do this operation row by row is going to be a function called rowwise. So if you add a pipe, there is a function called rowwise that tells the data frame that everything we're doing next is going to be row by row. All right, so let's add a pipe. The first thing I want to do here is calculate the mean of those three columns for each row. So we're going to come here. How do we do that? How would you calculate the mean of those three values? And I'm in this case, because we're doing row-wise for the first time, there's going to be a little bit of a difference, so I don't expect you to know everything. But maybe what will be the function that we need here to start off? Mutate. All right. Thanks, Aman. So mutate, I want to call this mean underscore pixel. And then we're gonna, because we want to calculate the mean of those three values, we need the mean function, right? So we call the mean function. And here what we want to tell it is I want the mean of these three columns, but on a row-wise pattern, right? So here inside of mean, we have to use the C function to give three values. And I want to say inside the C function, sy17, comma, sy19, comma, sy20. So that is going to calculate the mean on a row-wise pattern of those three columns. And that calculated mean for each row is then going to be under this new column called mean pixel. So if you run that and you print it and you navigate here to the right, now we have a new column saying mean pixel, which again, on a pixel, on a row basis, so 92.96 is the average of 98.5, 89.3, and 91.1 on a row-wise pattern. All right, so the next thing that we need is the coefficient of variation. However, if you remember, there is no function for that in R or Python. For some reason, that's just not a function that ships with R or Python. But we know the formula to calculate CV. What are the two pieces of information that you need to calculate coefficient of variation? Okay, so Amandeep said standard deviation and mean. So we have the mean already. Let's calculate the standard deviation. So I'm going to put a pipe here. It's called mutate. I want to call this SD underscore pixel. And there is a function called SD for standard deviation. So then in here, if you want to copy, you can. If you want to type, you can. But basically, we just need to give, again, that C function sy17, 19, and 20, which are the columns of which we want to calculate the standard deviation over. If you run that and print it, now you have a column with the standard deviation, and notice how it changes for different cells or different pixels, which is what you would expect, right? We have a different type of variability of standardized yield across each one of these cells. And now finally, we have everything we need to calculate CV. So let me ask.
Dr. Bastos, I have a question.
Yes, Paulie.
I was running the mean, and right now for the mean pixel, it's NA, and I run it, and the LR is giving me, it's saying that the argument are not numeric, or the logical it's returning NA.
Okay, so Paulie, first off, so you were able to do it until row-wise, right?
Yes.
Okay, so if you stop the flow right before that pipe after row-wise and run it, and print SY all, what I think it may have happened for some reason is maybe your SY 17, 19, and 20, maybe they're not double. They're not, one of them is non-numeric. Which one?
Right now they're all double.
They're all double.
Yes.
Okay, and you were able to calculate the mean pixel?
Whenever I try to calculate the mean pixel, that's why I'm getting the NA.
Okay, so make sure that you have so make sure your code is just like mine. But one of the things I would try is make sure that you're using the mean function, and that inside the mean function you have the C function, and that you specify SY17, SY19, SY20, all separated by commas,
Yes.
and that you close all of your parentheses here.
Okay, it's now working.
What could you share with us what happened?
For the SY17, there was a comma in between the comma, and those for all the SA. I think that was the issue.
Okay,
I
so
was using the old function, the SA/17, instead of using the column called SY17.
gotcha. Yeah, so you were specifying a column that it didn't exist, pretty much.
Yes, yes.
Awesome. All right. Okay, so now we have the mean, now we have the standard deviation. Can someone in Tifton help me? How would you calculate the CV? So I'll give you the pipe to get started. How would you calculate CV?
The same way, but with the formula CV. Ah, no, because you have to.
Yeah, we don't have a formula for CV. So, well, Benedetta, what is the function, I guess, that we're going to start off with?
Mutate.
Mutate, right? So let's do mutate. I want to call this CV underscore pixel, just so we all have this standardized. And then, well, you may not remember the CV formula, but the CV formula is basically SD underscore pixel divided by mean underscore pixel. Is the standard deviation by mean is what coefficient of variation is. I want to wrap that around parentheses so I can multiply by 100. And then make sure you close the final parentheses here to close the mutate. And that's it. So now we have our SY 17, 19, 20. We have the mean. And then finally, we have the CV of that mean. That's all we needed. And again, you don't know all this yet because you have not read the paper, because I have not given you that assignment yet. But what we need to then now create categories of stability is basically the mean value and the CV value. That's all we need from this point on. Before we do that though, let's do some EDA here. So this is kind of interesting because normally we do EDA in the beginning, right? But because we built so many different things here, I want to do some EDA on what we built. So the first thing I want to look into is what is the variability of the CV in this case. So if you just run that, this is how our CV is ranging. So it's going from basically almost 0. In that case, the 3 standardized yield values for those pixels were really similar, right? So a very low CV. We don't know yet if that was similar because it was all low or because it was all high yielding, but at least it was similar. And then the CV is going all the way to 75%. In research, as a general rule of thumb, we would say that a CV of 10 to 15% is acceptable. Something greater than that is variable. Look at that. We have one that goes all the way to 75% CV. So a lot of variability. So probably this pixel was high yielding sometimes, low yielding other times, and therefore the CV is so different. So we have, potential in this field here of some areas being very consistent, both on the high side or on the low side, but also some cells that really change, depends on the year. Sometimes they're high yielding, sometimes they're low yielding. So that's also interesting from a precision ag perspective. How do you treat them? Right? So we're gonna get to that conversation in a different part of this exercise, but I just wanted to introduce that idea. Okay, so let's make a few plots here. The next one that I have for us is I want to look, so right here, we're looking at the statistical distribution of the CV in a tabular format, right? I want to visualize that on a density plot format. I want to see that plot. So let's create that plot right here. We're going to start off with ggplot, add a plus. Well, maybe inside, sorry, before we add a plus, inside ggplot, I want to specify the data and the AES. So data is going to be equal to SY all. That's a data set that has the mean and the CV. Give a comma, break line, AES. I want, on the AES, I want to say that on the x-axis, I want to see this, the mean, wait, the CV underscore pixel. That's what I want to see. And then we add a plus and bring geom density. Also, I want to add a plus and bring geom rug. So he adds a vertical little bar every time there is a point on that distribution. So if you do that, look at this. It's a skewed distribution, right? Just like we were talking about before. So the CV, there is a concentration of CV values around maybe 8, looks like. And then he has a long tail with a point that is all the way out to 75, as we saw before. You know, let me show you something here that I think is actually very interesting for us to notice. So in this case here, where this distribution is skewed, right? We have a long tail to one of the sides. Look at how the mean and the median values are different. I mean, it's not by a lot, it's just like 2% on this percent scale. But the median is lower than the mean. So the median is around 9. So this line here is 10. The median is probably closer to the peak. But the mean is a little bit to the right, is after this vertical line. And that's what I was explaining to you earlier. In distributions that are non-normal, meaning that they have a long tail to one of the sides, the mean and the median start to deviate from each other. And the more points you have towards that tail, the farther out the mean is going to be. The farther away the mean and the median will be. And the median is not as affected by those outlier points. So the median would not move as much as the mean would because of this long tail. I think that was a good point for us to make on this plot as well. All right. Now I want to look into, so we calculated on a pixel basis, we calculated the mean standardized yield and the CV of each pixel based on that standardized value. I want to make a plot of those two things. And again, I want to assign them to an object so we can bring them together later. So let's do first the plot of the mean. If you come here, we're going to use ggplot. We add a plus. So our object is this SY all. I just want to print it below here so that plus is not going to help me. If I just print it below here, this is the object that we want to use to make this map. What is the geom that we need here? What do you think, Mohit?
uh, geom
So what, if you're not sure, how would you find out if you're doing this on your side and you have to figure this out yourself?
To see the object.
You check the object, right? So SY all, if we printed and we come on the first panel here, this is a simple feature collection. Another way as well to be more explicit is to use the function class. So class of SY all is an SF object. So what geom would you use here?
GeoMSF.
Yes, right. Thanks, Mohit. All right, so geomsf, we're gonna say data equals SY underscore all. The way that I want this to work is I want the fill of those pixels to be according to the mean. So if I print again the object SY all, I want the pixels to be colored or filled in this case according to mean pixel. How would you do that, Polly? What do we need here?
Fill equal mean pixel.
Mean pixel. Is that it? We can try. Okay, mean pixel not found. So the error doesn't really tell you why this happened, but we're missing something here. What do you think it is, Luke?
Oh, actually, I'm not sure. I was thinking it was the under fill you had to specify you know, SY all again and then give the $sign, but I'm not sure actually.
I think I know the issue. What about the AS, the
Yes.
aesthetic?
Yes, Polly, that's right. So we're missing AS. Remember that every time, so I say this a lot, it's probably going to be a next exam question. So make sure you all get this. Every time you want to change color, fill, size, transparency, according to values of a column, that's the key word here. According to values of a column, it has to go inside AS. AS is what connects that visual aspect with a column. Okay, so we need AS here. We need to wrap fill equals mean pixel in AS. So if we run that and we printed, oops, sorry, I'm printing the data set. That's not what I meant to print. Print the object. This is our map. Let's change a few things here. So the first one is I want outside of AS, I want to remove the outline of these pixels or cells. We've done that before. We say color equals NA. So that removes that black outline and lets the data, the fill data come through a little bit better. And now I want to use a different color scale just for us to maybe like keep the color scale that we're using before for the standardized yield across time. And now I want to use a Viridis. So let's do scale, fill, Viridis. We can use the B Viridis for bend. I want to change the option of the color here to option equals uppercase C. So this is, it changes to this look. And then I want to have our breaks change as well. So inside scale fill Viridis B, let's say breaks equals to C function 80 and 120. So basically we're going to have three colors. One that is 80 or less than 80% of the median, between 80 and 120, and 120 or greater than that. These are the scales that we created here for this plot. Okay, so let's interpret this. How would you interpret this plot here? So let me ask, let's see, Amandeep.
Is more like this increase in mean on the yellow.
Okay, so the yellow is 120% or greater than the median. right? So that's what the yellow points represent here. So where are the high yielding points average over 3 years happening on this field?
Which are yellow, like pink to yellow.
Mm-hmm. So more like on the southwest side of this field, right? Okay. So notice that now we don't have the 100% on this scale, and there is a reason for that. It's not a bug, it's a feature. But there's no 100% on the color scale that we are creating here. So we cannot fully compare directly with what we did before on the maps before. But notice that this is the mean pixel, right? So it's the mean standardized yield over 3 years. So we could say that everywhere that's yellow, that's 120% or more, has had a pretty high yield over time. And then between 80% and 120%, maybe let's call that medium yielding according to the median. It's really what dominates this field, right? A lot of it is in between 80 and 120% of the median on average across 3 years. And then as we had already learned visually, these areas here in dark blue have had low yields across all 3 years, potentially. So we can really see that pattern. Now, notice again, this is not a map about one single year. This is the average across all 3 years. So it gives us some indication of how the average yield has changed over 3 years. However, this is the average yield. This map does not give us an indication of the variability. Perhaps 1 pixel here of the medium yield, so the pink color, maybe one of these pixels was like 100, 101, 99. Pretty tight, pretty low CV. But maybe another one of these pink ones was 181 year and 60 on the other. So very variable. So by looking just at the mean pixel does not tell us how variable it was. It just tells us what's the average over time. And that's why we create the CV pixel. So let's see here. Let's do the following. We're actually over time already. Sorry. Let's stop here. I don't want to rush this too much. No, okay. So let's do this. I'm gonna open here the attendance. If you have to leave, just claim your attendance and go. As long as you respond to attendance, that's what matters. So let me come here. So the assignment is going to be due next Monday. Yeah, we also have to talk about that. So let me just do one thing at a time so I don't forget. New issue, attendance, February 20th. All right, so if you have to leave, you're welcome to. I know I'm over time, but I think it's worth it just to spend another couple minutes to finish this next chunk, because that's going to be a good stopping point. So if you need to leave, claim your attendance and go, and then make sure you catch up the last couple minutes afterwards in the recording. If you can stick around for another couple minutes, let's do that. So to do our CV, so we have the map of the mean at this point. I want to do the same map for the CV. So let's basically copy the ggplot that we did for the mean, and let's just use that and edit that instead of typing everything again. So copy that ggplot from the mean, come back to the CV chunk and paste it. One difference here is that the fill now, we want it to be according to CV pixel instead of the mean pixel. And then the breaks, we want to change as well. I just want to have one break, so we don't even need the C function. And the break is going to be at 30. So 30% is going to be the break point. If you run that, and we print this map, this is what it looks like to us. So let me try to find a way for you to see both the code and the plots. So basically, for pixels that have a high CV, so the variability from year to year is high, they are here in pink, in yellow. And for pixels that have a lower than 30% CV, they are in blue. As we see here, majority of the field is less than 30% CV, but they're all everywhere that you see a yellow dot, that pixel was variable, right? And we see where that is happening in space. So there's that little pocket on the north side. There's a few points here close to the gullies, and then some other scatter points as well. Now, the next thing I want to do is combine both of these maps. So SY all mean and SY all CV into one, and then save that with ggSave. So just make sure you run that, and then you're gonna have that in your saved on your files on your output folder here. If you go on the files tab, output folder, it's gonna be right there. All right, so we're gonna wrap up here, which I think is actually worked out really well, because the next step we're gonna be doing is exactly related to the paper that you're gonna read. So let's do this. For the exam, I will expect you to be familiar with the paper. And so we're stopping today at the content, and then whatever is on the paper is fair game. Everything we do, at least in class on Tuesday, is not going to be part of the exam, but the paper assignment will. So I have an assignment here. I pushed that to GitHub. So whenever you got GitHub for today's class, you also got the assignment as well. So if you go here on our GitHub, I just went on your machine already, on your computer, I just want to show you that. So under 02 assignments, there is an assignment 7 yield stability paper. I basically want you to read this paper. And then after or during reading or after reading, I want you to answer some questions for me. Maybe you can like take a look at the questions first and then read the paper, because that's going to help you to understand what parts of the paper you need to answer the questions. But these are all questions related to the paper itself. It should be pretty straightforward. Once you answer them, you know, render it and then upload to EOC the HTML of that. You have until Monday, 11:59 p.m. to do this. And then on Tuesday, we're going to be implementing what you read on that paper using these metrics. All right, I know I'm way over time, so let me stop here. If anyone has any questions about anything, I'm going to stick around for a couple minutes. And if not, then you're dismissed, and we will see you on Tuesday.